Welcome back to General Chemistry. This is General Chemistry 2, so we are going to review a little bit of what you have already learned in General Chemistry 1, that being Lewis structures. So let's do these as an example and see what we can remember, see what we can recall, and then we can go forward to some of our new stuff that we're going to learn this semester, which I'm really looking forward to working with you on. So to begin with, what is the Lewis structure for sulfur? Well, first off, this is referring to the element sulfur. And so with sulfur, all you got to do is you got to look at the periodic table, figure out where it's located on the table, and then figure out how many electrons it has. So sulfur has 6 electrons. So we draw an S with 1, 2, 3, 4, 5, 6 electrons all around it. And there you go. That's as hard as it gets. So there's our Lewis diagram for an atom, a sulfur atom. Next is our calcium ion. And so if you look at calcium, calcium is in the second column going down, which means calcium has a 2+ charge. How did it get a 2+ charge? It lost 2 electrons. So elemental calcium should have 2 electrons, but we turned it into an ion, so it lost those electrons, which means now we represent it as an ion with brackets and the charge written outside of the parentheses. And so that's kind of a good way to remember how to do these is your cations. Remember that term, your positively charged ions? Your cations typically don't have any electrons around that central elemental symbol. Why? It lost the electrons. Whereas your anions are typically going to have a full octet with 8 electrons drawn around the elemental symbol, with the charge always on the outside. So here we have an example of a cation, calcium, Lewis structure. Next, silicon tetrafluoride. So we've got silicon and we have tetra, so that means we have 4 fluorines, or SiF4. Remember your naming. This is going to be pretty crucial because I'm not going to really slow down to be like silicon tetrafluoride. Tetra means it's covalent. Covalent, tetra means 4, so SiF4. Or if you've got things like sodium nitrate, polyatomic ion. Sodium is a metal. Anytime you have a metal, you're going to have an ionic bond here because nonmetals form covalent compounds. A metal plus nonmetal, or nonmetals, plural, is going to be an ionic compound. And so here, carbon monoxide, covalent. So these are good things to remember. So here we've got silicon tetrafluoride. Silicon, it is right underneath carbon, so it has 4 electrons. So we have 1 atom times 4, because it's got 4 valence electrons natively, right underneath carbon. Fluorine, if we find it on the periodic table, there are 4 of them in this structure. And then how many valence electrons does fluorine have? 7. So 4 times 7. All I'm doing right here, this little math, is to tell me how many electrons do I have available to put on my Lewis structure. So here we have 4 times 7 is 28 plus 4. So I need to make sure at the end that I need to put 32 electrons all around my structure. Okay, so I know I have a silicon, and I know I have 4 fluorines. Which one goes in the middle? Remember, the least electronegative goes in the middle. So that is silicon, and then fluorine goes all around it, and then we fill in our electrons. The very last thing we need to do is check and make sure that the electrons we've drawn matches the electrons we have available for our Lewis structure. So 4 times 8 is 32. Check. We're complete. So there's the Lewis structure for silicon tetrafluoride. Next, my oxygen molecule. Remember, there are 7 atoms that are diatomic at room temperature. And so if you go to your periodic table, and you start at nitrogen and you go over oxygen, fluorine, and then straight down, 1, 2, 3 more elements, that kind of looks like the number 7. And so those are your 7 atoms that are diatomic at room temperature, but then you also have to include hydrogen at the top. So oxygen molecule is diatomic at room temperature, and it's a gas at room temperature. So O2, and it's going to be a gas. What's the Lewis structure then? Oxygen, there's 2 of them, and it has 6 valence electrons. And so we have a total of 12 valence electrons available. So let's see, give it a try and see. Oxygen, if we just have 1 bond drawn, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 2 electrons left. If I just give them to 1, the other one's not happy. Because remember, you got to have a satisfied octet. That's what all of these elements are wanting to do. Either by losing electrons, like my calcium ion here, or by sharing, so that they can all have an octet like this for this covalent compound. Which means if I just add an extra covalent bond here, I've made both of my oxygens happy because they both have 8. And then total, there's 12 valence electrons drawn. So the amount I've drawn matches the number that I have available. So this is my Lewis structure. I made those dots a little easier for you to see. Okay, next is carbon monoxide. So we've got carbon monoxide, CO. How many electrons are available? This carbon donates 4 plus 6 for oxygen, means I have 10 valence electrons available. So what if we try drawing it like this? Carbon, 1, 2, 2, 4, 6, 8, 9. So what if we try drawing it like this, where we've got a triple bond? I see this a lot whenever I Google it. So I've got a carbon with 1, 2, 3, 4, 5, 6, 7, 8. So carbon's happy. Oxygen, 6, 7, 8. Oxygen's happy. And do I have 10 drawn on the whole compound? Let's see. 8, 9, 10. Yes, so it's happy. But I've also seen this drawn like this, where carbon's not happy, right? Because it has 6, it should have 8. Here, oxygen's happy because it has 8, 9, 10. There's a total of 10 valence electrons drawn. Which one is more stable? Which one is the best? This is where we get into that formal charge analysis. Do you remember what I'm talking about by formal charge analysis? It's where you go formal charge equals your valence electrons minus, dots minus lines, meaning your non-binding electrons and 1/2 of your bonding electrons. And so this formal charge analysis, what it's trying to ascertain is where is the predominant amount of charge present on this molecule. So if we look at this structure here, what is the formal charge for carbon? Carbon has 4 valence electrons, 4 minus, how many dots does it have? 2. How many bonds does it have? 3. So the formal charge for carbon is 4 minus 2 minus 3, which is -1. And oxygen has 6 valence electrons minus 2 dots minus 3 lines, which means it has a total charge of +1. Does it make sense that the more electronegative compound is going to have a positive formal charge? Absolutely not. That doesn't make sense. Why would oxygen allow carbon to have more of the electron density? It won't. Is it solved in this case? Let's see. Formal charge for carbon is 4 minus dots is 2 minus lines is 2. 0. What about oxygen? 6 minus dots is 4 minus lines is 2. 0. So see how in this model, the electron density is actually more equally shared between the two atoms. And so that would be the more stable Lewis structure. And so I just wanted to remind you about formal charge analysis as we looked at carbon monoxide as an example. Okay, next, let's go down here to sodium nitrate. I know I've taken up a lot of my board, so I'll kind of draw a line under here so that we can see how they're separated. So sodium and nitrate. You should remember that sodium is Na plus, nitrate is NO3 minus, which means our sodium, we can represent it by Na brackets plus. Our nitrate, on the other hand, is going to need a little more space and a negative. We know that nitrogen's in the middle because the least electronegative is in the middle. We know there's 3 oxygens all around. But how are they connected? Is it double bonds, single bonds? Well, let's find out. All right, so first off, let's see how many electrons we have available to put on our molecule. Nitrogen, it's got 5. Oxygen, there's 3 of them, and there's 6 total per oxygen. And then we have +1 extra of our charge here. So nitrogen is 5, plus 3 times 6 is 18, plus another 1. Let's see, what is 18 plus 6? That's 24 electrons. With 24, that tells me I need 8 around each one of my oxygens, which is great. But I could accomplish that with a single bond and then electrons around it, 2 pairs. Or I could do double bond in 2 pairs, or a single bond in 3 pairs. It just depends on which one's more stable. But if we come here to this formal charge analysis, that's going to tell us exactly how many single and double bonds we need. Let me give you an example. Formal charge on a single oxygen, so a double bond, that would be 6. Valence electrons for oxygen is a 6 minus my dots. So if I had a single bond oxygen, let me draw this right here just so you can see it. Oxygen single bond looks like this, whereas oxygen double bond looks like that. So a single bond oxygen has 1, 2, 3, 4, 5, 6 dots and 1 line. So that's -1. Whereas the formal charge of a double bonded oxygen is 6 minus my dots here is 1, 2, 3, 4 minus 2 lines equals 0. So what that tells me is if I want a -1 charge, I need 1 single and 2 doubles. 1 single, 2 doubles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll make these bigger so you can see. Kind of on my line there. There should be 6 electrons going off here. So now I've drawn 8, 16, 24. This is the most stable and the best Lewis structure. There is resonance about this because this single bond could be on any of the oxygens. There's no reason it needs to belong to this one as compared to this one or vice versa. All right, and with that, we have reviewed a lot of covalent Lewis structures and a lot of, ions and some atoms, but it's up to you now to practice. And so the rest of the worksheet that you've been given is just practicing this.